Hi, this video is the final presentation for the Capstone project within the IBM's Advanced Data Science specialization on Coursera. My name is Vitalii Vorobiov, and I'm going to present you my case. So within this project, the students were supposed to choose a sample data set and create a final data product for a hypothetical use case. The task itself was to go through all the typical steps of a regular data science project, starting from data exploration and cleansing, preparing data for machine learning, defining machine learning or deep learning models, evaluating their performance, and coming up with the final result. So let me start with a presentation I've done for my theoretical stakeholders, which also contains some basic details about my use case. Automated credit risk detection is the name of my project, and it explores the use of machine learning algorithms to automate issuance decisions for private crediting sector. So the problem was that assessing credit risks manually is a time-consuming task and requires lots of efforts, and it contains many parameters that are not obviously connected together. So for a financial institution, it would be a great project to try to automate this decision-making process and have the prediction for this credit risk based on parameters. So here is the example of the data. This is a CSV file that was provided by this theoretical banking institution, and it was very diligently collected with all the risks labeled. So that means that we would be in a supervised machine learning environment. So this presentation is intentionally very basic, so I stop at this data structure picture and then switch to the presentation for the peers. But let me talk a little bit about what parameters, what values, what data do we actually have. So each record is the information about a person that would like to have a credit by the bank. So it contains personal information like age and gender, first of all. Then it's some info about the financial situation of a person, like whether it has a house or rents one or nothing at all, like professional skills, skilled or not, because it influences the income opportunities. And then saving accounts and checking accounts of how much money is there already. Yeah, and then there is a purpose. So the purpose can be car, furniture, repairs, probably for some business or education or even vacation. So yeah, something of this kind. And then we have the credit amount and duration. Credit amount, so how much money does a person want, and duration for how long. And all this information leads to a decision. Bad risk means we don't issue credit. Good risk means okay, everything's okay, go on. So yeah, this is the scenario. Let me switch to another more detailed presentation. Okay, yes, so the first step is data exploration. So we can look at the age, for example, and identify some bins, categories. So from 18 to 25, for example, or 30 to 40, and so on. And if we look at duration and credit amount, we can identify some obvious outliers. Then I tried to transform some information into a more natural records, and I joined some So professional, gender, and housing situation together, and made two diagrams for the bad and the good risk. And what we see from here is that it's actually the same pattern. So skilled male with own house are the most likely to receive a good risk, but they're also the most likely to receive bad risk. So they're the first for both groups. I've also made this correlation heat map, where we can actually see that only a couple of parameters like gender are dependent, correlated, and probably some job types. But otherwise, there's no correlation between all of these data. So, of course, I've made much more visualization, but I stick to just some of them in this presentation. But all this information and all this data exploration just leads to the decision that basically all the parameters should be used as features. So after the actual exploration of the data, we just proceed to extract transform load. So the CSV file goes to a nice Panda data frame, and then we see that there are some missing values. We make some data cleansing, filling in some missing values, and then we get these nice looking data frame that's actually suitable for proceeding to models. Actually, as was already said, just want everything to go into features. So every single column. For that I use dummies. So all the columns were one-hot encoded, and the risk column was labeled. And then I actually switched to PySpark and used the very nice vector assembler and normalizer to transform everything into one single feature, normalized features column. And that's basically it. So after that, we can proceed to defining models, testing them, running and testing them. So before we go to actual models, we need to define the test sets. And in my case, I used random split and made the 80% for test data and 80% for trained data and 20% for test data. And as evaluation metrics, I used SparkML's multi-class classification evaluator with accuracy as the principal metric. So as I actually don't know which model would be better, I decided to compare three of them. And we have random forest, one versus rest, and gradient boosted trees as the one that were chosen. So these all should serve well in a supervised machine learning scenario. Let us see. So the first run was finished with these results shown on this diagram. So random forest went up as high as almost 90%. One versus rest was not that good. It was like 76. But the gradient boosted trees was really good, and it achieved right from the start without any tuning 97.5%. We already have a good result. We can just continue with gradient boosted trees, but what I wanted to try is to improve these models, and for that I took random forest and gradient boosted trees together. So that cross-validation and hyperparameter and research techniques were used. So that's also called hyperparameter tuning. And here's a portion of code for random forest and for gradient boosted trees. So the results were quite impressive because the models went from this 90% random forest to 96, more than 96, and gradient boosted trees actually went up to 100%. But then we made a second iteration and actually dropped the gender column because it was highly 100% correlated and probably doesn't influence result, or maybe is just extra. It's not required. The improvement in the results was not that great, but actually even the random forest went up to 100% accuracy, which is absolutely fantastic. So that's basically it. You can find all the details in my submission, as well as ADD document and links to the notebooks. And thank you for watching. I hope it was not too boring, and I wish you all the best with your own data science projects.